The chip model that we talked about in the previous section can be really useful for representing or modeling multiplication of integers. So here, let's just stick with positive integers first. And so this should not be too unfamiliar to you right now. So 3 times 4 we can represent as 3 groups of 4. So here I have a couple of groups of 4. I have 3 groups of 4. And we can repeatedly add these groups of 4 together to get 3 groups of 4, or 3 times 4, which is equal to 12. Right? So this is equal to 12 because we have 12 of these chips here. And these are all positive chips too, so this is going to actually represent the number positive 12. Okay, so here we're repeatedly adding groups of 4s. So keyword add right there. That's going to be relevant very soon. All right, so we could also use negative chips to represent this as well. So here we have 3 groups of negative 4. So we're repeatedly adding groups of negative 4. Each of these groups has 4 negative chips in it, and we combine them all together and we end up with 12 negative chips. And so 3 groups of negative 4 is equal to negative 12. We're repeatedly adding groups of negative 4 because this we're adding that many times, and this is what we're adding. All right, so what if we wanted to, say, reverse this? So like instead of 3 times 4, represent it as negative 4 times 3. So this represents the same sort of thing, but in a different way, right? Or if we wanted to do like negative 3 times negative 4. Negative 3 times negative 4. How do we represent that? So let's do negative 4 times 3 first. Let's first think about how can we interpret the first number as being negative in this. So instead of repeatedly adding 4 groups of 3, so if this were positive, then we'd be adding 4 groups of 3. Since this is negative, we're going to repeatedly take away 4 groups of 3. Right? So we're repeatedly taking away groups instead of repeatedly adding them. So what do we take them away from? Well, we'll take them away from the number 0. 0 is like our base starting number. And if we want to repeatedly take away 4 groups of 3, well, there has to be groups of like 4 groups of 3 to take away. And so what we do is we represent the number 0 in a different way. We represent it by introducing a bunch of these canceling pairs. The positive and the negative chips make a canceling pair, remember? And so we introduce 4 groups of 3 of these canceling pairs. So this is 1 canceling pair, this is 3, this is a group of 3 canceling pairs, and then we introduce 4 groups of 3 canceling pairs. And then, now that we've represented the number 0 in this way, we will now, for this last step, we will take away 4 groups of 3. And so if we're taking away 4 groups of 3, since we're taking away groups of positive 3, we want to take away these positive chips. So that's 1 group of 3 we got rid of. This is another group of 3 we got rid of. Third group of 3, and this is the 4th group of 3 that we got rid of. And so what are we left with after we've taken away 4 groups of 3? We're left with 12 negative chips, or negative 12. And so negative 4 times 3, we can see with this model, is equal to negative 12. All right, what about negative 4 times negative 3, now that we've kind of built up to this? So again, we represent the number 0. Well, we start with the number 0, and then we represent it with a bunch of canceling pairs. So we introduce 4 groups of 3 canceling pairs here. And then we repeatedly take away 4 groups of negative 3. So we're taking away 4 groups of 3 negative chips. So that's 1 group of negative 3, that's 2 groups of negative 3, 3 groups of negative 3, and 4 groups of negative 3 that we have taken away. And so what are we left with? We're left with 12 positive chips. And so negative 4 times negative 3 is equal to positive 12 via this model. All right. How do we think about division with integers? So we're not going to use models to discuss this. We're going to just think of this a little bit more algebraically. So negative 6 times 2. So in the same way that we would think of 6 divided by 2 as like what number, like 2 times what number is equal to 6. It's like a missing factor problem. And so what number multiplies by 2 to give you 6? Well, that number would be 3. And so 6 divided by 2 would be equal to 3. Right? So same sort of idea is going to apply here. 6 divided by 2, we want to think of this as 2 times what number is equal to negative 6. And so using what we already know about multiplication, this number has to be equal to negative 3. So via this like missing factor approach, we can say that that's equal to negative 3, and we could do this in other situations similarly. So 24 divided by negative 6, what number multiplies with negative 6 to give you positive 24? Well, 6 times 4 is 24, and so we're going to want negative 6 times negative 4 is equal to positive 24. And then similarly for this last one, negative 30 divided by negative 5 equals what? So negative 5 times what is equal to negative 30, and so that number is going to be 6. All right, cool, nothing too special with that. All right, last thing I want to talk about in this video is going to be negative exponents. All right, so let me get rid of that. So let's first kind of think of positive exponents again. So forget what's going on down here for a second. So we know that like a cubed, we can represent it as like a times a times a. A squared is just like repeatedly multiplying a 2 times. I forgot a 1 right there. A to the first is just equal to a to the 0 is equal to 1. So we're repeatedly like multiplying by a to get to whatever like the next highest like exponent or power of a is going to be, whatever. And so to move backwards, you can instead divide by a. So to get from a cubed to a squared, you divide by a. Divide by a from a squared to a to the first, and then divide by a to get to a to the 0. And so if we extend this pattern, so every time you divide like a to some power, divide that by a, that's going to lower your exponent by 1. So when you get to a to the 0, if you want to get to a to the negative 1, you just divide whatever a to the 0 is, divide it by a. And so if I divide 1 by a, what do I get? I just get 1 over a. And if I divide 1 over a, divide that by a, that's going to give me 1 over a squared. And then to get from a to the negative 2 to a to the negative 3, I just divide 1 over a squared by a, and I'm going to end up with 1 over a cubed. And so we get this, you can kind of take it as a definition. A to the negative n is equal to 1 over a to the n. All right, so you might wonder, does this only work for like positive values of n? Like, does this work for negative values of n? And the answer is yes. So for example, if like n is equal to negative 2, then a to the negative n would be a to the, so negative n is really the opposite of whatever n is. So this is like negative 2 or a to the positive 2. And is that equal to 1 over, put a question mark here because we're wondering if this formula is true. Is that equal to 1 over a to the 1 over a to the n, which would be a to the negative 2. So is a squared equal to 1 over a to the negative 2? Well, 1 over a to the negative 2, you could think of that as 1 over a squared. And then when you are like, when you have something like this, let's see, maybe I can rewrite this a little bit more clearly. what you can do is multiply by a squared over a squared. And so you're left with a squared in the numerator. And in the denominator, you get 1 over a squared times a squared, which is just equal to 1. So that is actually equal to a squared. And so this question mark is no longer a question mark. We know that it's actually going to be true. So yes, this formula works for all values of n. All right, cool. I think that's all I want to talk about in this video. In the next one, we'll talk about ordering integers.